Bismillahirrahmanirrahim. Welcome to the next lecture of the course Software Defined Radio. In today's lecture, we are going to talk about the link budget and receiver sensitivity calculations. In the lectures so far, we have been talking about the RF frontends. We have discussed the various architectures of RF frontends, and then we had a detailed discussion on the various RF impairments. The discussion on these RF front ends is almost coming to an end now, and today we are going to start a topic which is crucial in order to understand the working of a wireless communication link. The link budget analysis, basically, it is concerned with the several important parameters of the channel and the transceiver that eventually determine the performance of the link. So we are going to learn whether or not the link is going to work or not. How much will be the communication range, for instance? How much will be the expected bit error rate? How much should be the transmit power? How much should be the noise figure of the receiver? How much should be the antenna gains, and so on and so forth. So these are all the factors which eventually determine the performance of a communication link. And let me first of all try to formalize it, write it down. So these parameters include, to start with, the TX power. Then we have carrier frequency. We have the channel bandwidth. By channel bandwidth, we basically mean not only the bandwidth of the signal, but also the bandwidth that passes through the transmit and receive chains without much attenuation. So this basically means the passband of the receiver circuitry. So that will be the channel bandwidth, and typically the channel that you are using is reserved for you. There is not much interference, and the neighboring channel is being used by some other user. Then other parameters that affect the link budget calculations include the system noise figure. Towards the end of the previous lecture, we talked about the noise figure. Today we are going to detail that discussion a bit more. Then other parameter that this performance depends upon is the communication environment. And what else? It also depends upon the TX and RX antenna gains, the temperature of the device, and one of the most crucial is that it depends upon the required SNR. Whatever modulation encoding scheme that you are using, how much is your required SNR is going to determine the link performance. And then there are some additional margins for fading, imperfect implementations, and etc. And now, with all these parameters written explicitly in front of you, you will be able to realize that all these parameters are going to eventually impact and determine the performance of a wireless communication link. So whether the transmit power should be increased or reduced, or is the transmit power sufficient enough, is going to determine the performance. Similarly, the carrier frequency is going to play its role. The channel bandwidth plays a vital role in terms of the effective noise power that disturbs or corrupts the signal. Then we have the system noise figure, the rise in the noise floor that occurs solely due to this device, and the communication environment, which can be a wired communication link. In a wired communication link, it is the most simplest communication environment. But if it's wireless, there are going to be other signals that are present in the environment. There is going to be ambient noise, and there are other sorts of imperfections like multipath propagation that impact your communication performance. The transmit and receive antenna gains impact your performance. The temperature of the device determines the noise floor. The required SNR is crucial, and additional margins for fading in imperfect implementation. All in all, we are going to learn the impact of all these parameters on how we can use them to predict the performance of a communication link. So we are going to start. We are going to have today's lecture in few parts. So there will be a discussion of various items, and towards the end of the lecture, we will see how all these discussions combine together to form what we refer to as the receiver sensitivity calculation, and then eventually how all these discussions that we are going to carry out in today's lecture eventually help us to do the link budget calculations. So now we start with the first one. And the first topic that we are going to discuss today is referred to as path loss. To understand the discussion of path loss, you can imagine this an arbitrary transmitter, and there is a receiver. There is going to be wireless communication between the transmitter and receiver. The communication takes place via electromagnetic waves, and these waves propagate with the speed of light and following the principles of Maxwell's theory. We are going to imagine that the transmit antenna radiates some waves, and these waves then propagate in the environment until they reach the receiver. The amount of power radiated by the transmit antenna is referred to as here as PT, and the amount of power that is being captured by the receive antenna will be referred to as PR. And you can well imagine that PR will be much lower than PT. Why so? PR, the received power, will be lower than the transmit power because a lot of the power is also radiated in other directions. And only a fraction of the power that is radiated towards the receiver is captured by the receive antenna. And that means, and how much, and this depends upon the portion of the receive antenna that is comparable as compared to the size of the sphere that is formed at this distance d centered around the transmitter. So if you imagine a sphere of this radius d around the transmitter, you can imagine that the amount of power that the receive antenna captures is only a small fraction of that. If d is the distance between the transmitter and receiver, the amount of power that we are going to receive at the receive antenna is proportional to 1 by d square. And this has to do with the surface area of the sphere, which is 4 pi d square. And if you compare, if the size of the receive antenna is fixed, the section of the sphere that is comparable to the size of receive antenna will be proportional to 1 by d square. And that is the main intuition behind this proportionality. So the received power is inversely proportional to the square of the distance. So this is the first relationship. Of course, PR will be proportional to PT. If you increase or if you double the transmit power, the received power will also be doubled. And another relationship that holds is PR is proportional to lambda square. And this is under the assumption that the receive antenna is also changing its size or its physical dimensions with the wavelength of the signal. If you increase the wavelength, the size of the receive antenna will be bigger and it will be able to capture more of the sphere surface area that will reach the receiver. So PR will be proportional to lambda square. If we combine all these proportionalities and try to write down the equation for the received power together with some constants of proportionality, the final equation that comes is as follows. PR is given as PT times lambda divided by 4 pi d whole square. So this is the equation of the received power. If you are transmitting with a transmit power PT and operating at a wavelength lambda, and the distance between the transmitter and receiver is d, then the amount of received power can be given by this equation. Note here that c, the speed of the light, is related to the frequency and wavelength by this formula. So if you're given the frequency, you can compute the wavelength, and if you're given the wavelength, you can also express the equation in terms of the frequency. Now this equation that we have just written is referred to as the path loss expression for free space. And by free space, we mean a space which is free of any obstruction or any object that can diffract, reflect, or absorb the signal. So you can imagine free space as the space, as the communication between transmitter and receiver, which are placed in a space, or in more real terms, placed on very high grounds. So if there is a direct line of sight between two mountains and there is a valley in between, the propagation model or the amount of received power at the receive antenna can be very accurately predicted by this equation. So this is referred to as the free space path loss model. In reality, if you are in a real life wireless propagation environment, then there are some additional elements to consider. And the main thing that changes is that the received power is no longer inversely proportional to the square of the distance, but it becomes proportional to 1 divided by d raised to the power of n, and n is greater than 2. N is referred to as the path loss exponent, its value equal to 2 corresponds to the propagation model for free space, and its value greater than 2 corresponds to more real-life wireless environments where there are some trees in the environment, where there are some walls and some buildings in the environment, and there are other obstructions like vehicles or forestation involved. In the presence of these real-life obstructions, the received power is then written or modeled typically by this equation, which is PR is equal to PT times lambda by 4 pi d naught whole square times d naught by d raised to the power of n. And n is the path loss exponent, as I just described earlier. Value is greater than or equal to 2. D naught is referred to as the far field distance. Typically, D naught is tens of lambda. So this notion of D naught comes into play because the electromagnetic wave propagation is different in the near field as compared to the far field. The model that we are writing above applies only to the far field. That is, D in the above expression has to be greater than D naught. So we are not allowed to use this expression of received power for small values of distances between the transmitter and receiver. When the distance between the transmitter and receiver exceed at least 10 lambda, then we should be able to accurately represent the value of received power via this propagation model. The path loss exponent typically varies. It is a value of n equal to 2 corresponds to free space path loss exponent. A value of n that ranges between 2 to 3, it corresponds to rural area where there are not much obstructions. There is clear line of sight between the transmitter and the receiver, and the transmitter and receiver are placed on high hilltops so that the line of sight is unobstructed. In urban areas, values of 4 to 5 are typical. Urban built up area, which includes cities with buildings, with high-rise buildings, and other obstacles in between. A value of n equal to 6 is referred to as the path loss exponent for office type indoor environment, where there are a lot of walls in between, and the degradation of received power with respect to distance is much more steeper and sharper. We can also visualize this trend in terms of such a graph. If we plot log of t on the x-axis, and we start with this free space path loss model. So I'm going to write that expression again. So PR is equal to PT times lambda by 4 pi d whole square. And we can also represent this in log domain. So PR in the units of dBm is equal to PT, taking log on 10 log 10 of both sides, we get this PT dBm plus 10, and this exponent of 2 and gets multiplied with 10 to lead to 20 times log of lambda by 4 pi minus 20 log of d. And now if you try to plot the PR in the units of dBm with log of d on the x-axis, you are going to see that there will be a straight line. As you increase the value of log of d, there will be a 20 units reduction for each unit increase in log of d. That is to say, the slope of the line will be minus 20, and it will be a line that looks something like this. Slope equals to minus 20. This is the path loss model for free space. And now if you imagine the expression that we wrote down for the more real life wireless communication environment, we said that PR is equal to PT times lambda by 4 pi d naught whole square times d naught by d raised to the power of n. And n is greater than 2, greater than or equal to 2. If we write this expression in the units of dBm, we are going to see that PR dBm is equal to PT dBm plus 20 log of lambda by 4 pi d naught plus 10n log of d naught minus 10n log of d. And if you now look at this part, you are going to see that with the value of n being greater than equal to 2, the slope of the expression of PR dBm versus log of d is now going to be larger. So if at the value of n equal to 2, it will be again minus 20, but at the value of n equal to, for instance, 3, it will be a slope of minus 30, and so on. So the received power will decrease with the increasing distance, no longer with the slope of minus 20, but with a slope of minus 30. So this is not so this was the black line that we drew earlier. It represents the slope of minus 20 in our diagram. And now let's try again to draw a line that varies with a slope that is considerably larger than this slope. So that will be something like this. This line has a slope equal to, for instance, minus 30, and it reflects the path loss or the received power variation with a path loss exponent of 3, n equal to 3. So what you can tell from this particular graph is that the received power is going to decay much faster as we increase the distance on the x-axis. So if we start from this some initial distance, the received power is going to decay slowly in the case of free space. But if the environment has a lot of obstructions, if the path loss exponent is 3, for instance, or even larger, the received power is going to decay much faster with the increasing value of distance. Note that in some literature on these path loss models, this expression for propagation loss under non-free space environment, that is with path loss exponents greater than 2, is often written in a more simplified manner with the assumption that d naught is equal to 1. In that case, PR, the expression for received power in PR can be given as PT times lambda by 4 pi square times 1 by d raised to the power of n. And the difference between these two expressions is that d naught equal to 1 cancels out the contribution in the denominator and the numerator of that expression, and this expression is now solely dependent. It has a very similar syntax as compared to the original free space path loss model. So instead of a simple d here, there is a d raised to the power of n by 2 placed here, and this can also be represented in the log domain, which would mean that PR dBm is simply equal to PT dBm plus 20 log of lambda by 4 pi minus 10n times log of d. And now if you compare this expression with the expression for the free space path loss, you will see that the only difference between the two expressions is this factor of n here, 10n, which eventually leads to slopes of, for instance, minus 30 for n equal to 3. For n equal to 4, the slope will be minus 40, and so on. So as the built-up area or the density of the obstacles in the environment increases, the received power decreases much more rapidly with the increasing distance, which is very intuitive. Now, during this discussion, you might have noticed that I am using the term path loss. It might have been clear to some of you, but for conciseness, let me mention that the factor PR divided by PT will be referred to as the gain of the power. So that is the power that you have at the output versus the power that you had at the input. Typically, this will be referred to as the gain of the received power. But typically, since the environment is lossy, the ratio PT divided by PR will be what is referred to as path loss. And in this context, if we say that PL, if we use this notation that PL is equal to PT divided by PR, and putting in the value of received power from the previous expressions, we are going to see that PL can be given as 4 pi d naught divided by lambda whole square times d by d naught raised to the power of n. And this will be referred to as the path loss. This can also be expressed in the units of dBs. So PL in the units of dB will be equal to 20 log of 4 pi d naught by lambda plus 10n log of d minus 10n log of d naught. And again, a simplified version of this path loss expression can be obtained if we put in a value of d naught equal to 1. In that case, this term would vanish, and this term would simply correspond to 20 log of 4 pi by lambda, which is the case in the free space path loss model. So I think that concludes the discussion on path loss. Now, the next topic that we are going to talk about in today's lecture is antenna gain. At both ends of the communication link, at the transmit and the receive, we employ the transmit and receive antennas to transmit and to receive the electromagnetic waves. These antennas can be isotropic, which means that the antenna radiates equally, uniformly in all the directions. These antennas are omnidirectional or non-directive. There is no directivity in these antennas. They radiate equally in all the directions, which means that they form a sphere of wave fronts around the emanating element, around the radiating element. Similarly, the isotropic antenna at the receive side receives energy or electromagnetic wave from all the directions equally. The isotropic antennas have a gain of unity. Which amounts to no gain at all. Now, once we have some directional antennas, with some directivity, which means that if we talk about the transmit side, these antennas are able to transmit electromagnetic waves focused in a particular direction. And in an example, you can imagine such a parabolic antenna. The parabolic antennas have the ability to transmit highly focused electromagnetic radiations in a particular directions, and similarly, a parabolic antenna at the receive side will be able to receive beams from a certain direction and discard the energy coming from other directions. These directional antennas are, because of their ability to focus the transmit power into a certain direction and to receive the transmit and to receive the prevailing power in the air from a particular direction, are able to provide a gain in the received power. The factor by which a particular antenna increases the received power as compared to an isotropic antenna is referred to as its antenna gain. The antenna gain of directional antennas is therefore greater than 1. We will use the notation GT and GR to denote the antenna gains at the transmit side and the received side, and a product of these, which will be GT times GR equal to G, capital G, will be referred to as the combined antenna gain. This can be interpreted as the factor by which the received power increases because of the use of directional antennas as compared to an isotropic antenna. In the presence of these directional antennas, For instance, the expression for the received power changes as follows. So if you imagine, for instance, the expression for the received power in free space propagation path loss model, we used to have pt times lambda by 4 pi d whole square. And now, because of the antenna gains at the transmit and receive side, we will multiply this by another factor g. So therefore g is the factor by which the received power increases as compared to that of an isotropic antenna. In reality, antenna gains of 2 to 3 dBi are typically provided by the quarter wave monopole antennas, and there are some more directional antennas like horn antenna or parabolic antennas, which provides antenna gains as high as 20 dBi or so. So dBi is basically 10 log 10 of g. So this is basically, this reflects the antenna gain that is offered by the antenna in reference to an isotropic antenna. So this I here is it denotes that this is the antenna gain with respect to an isotropic antenna. The isotropic antenna will offer an antenna gain of 0 dBi because 10 log 10 of 1 will be 0, and any number greater than 1 will lead to a positive gain. So the horn and parabolic antennas are typically providing, for instance, an antenna gain of 20 dBi. Continuing further, the next topic that we are going to discuss today is atmospheric absorption. Atmospheric absorption refers to the additional path loss incurred by the electromagnetic waves as they propagate through the atmosphere of Earth. And this additional atmospheric absorption occurs basically because of the humidity or water vapors in the air. This also occurs due to fog, due to rain, and due to snow, and due to other number of gases that are there that constitute the atmosphere of the Earth. So all these factors lead to some additional propagation loss on top of the path loss that we have discussed already. And this attenuation is typically expressed in the terms of P atmosphere will be expressed as, for instance, 0.1 dB per kilometer. So this value is just an example, but just to emphasize that how do we characterize the atmospheric absorption. 0.1 dB per kilometer would mean that if the distance between the transmitter and receiver is, for instance, 7 kilometer, there will be a 0.7 dB additional path loss due to the atmospheric absorption. The atmospheric absorption is frequency dependent. More precisely, the carrier it is proportional to the carrier frequency. So if the carrier frequency is, for instance, 100 megahertz or 200 megahertz versus the carrier frequency of 1 gigahertz, 2 gigahertz versus the carrier frequency of 20 gigahertz, they will all experience different levels of atmospheric absorption. There is no mathematical formulation to express this atmospheric absorption, but there are some plots that look something like this, and these are typically expressed obtained empirically by carrying channel sounding measurements over a real life environment, and they look something like this. if we have the atmospheric loss expressed in dB per kilometer on the y-axis, and on the x-axis we have frequency, the graph looks something like this. Which can be interpreted as, for instance, a very low value at low frequencies, but there are some spikes in the atmospheric absorption at certain distinct frequencies, and these frequencies then correspond to wavelengths that have some special relationship to the size of molecules of, for instance, various gases or water vapors. Right now, our main concern is not the exact plot, but I will share in the slides some example plots as well. Right now, the main focus of this discussion here is that there is a non-negligible loss in propagation due to the atmospheric absorption. This absorption occurs due to water vapors, fog, rain, or snow, and the loss is, generally speaking, higher at higher carrier frequencies. So this is the main theme, and typically if you say, let's say, the carrier frequencies of up to 1 gigahertz, this is totally negligible. Even till carrier frequencies of 20 gigahertz, the loss is less than 0.1 dB per kilometer under normal circumstances, and only in the region of millimeter waves, that is the carrier frequencies of 30 gigahertz and above, the atmospheric absorption increases to values like up to 1 dB per kilometer. Most noticeably, the spike of atmospheric absorption occurs at, for instance, FC of 60 gigahertz, where the path loss atmospheric absorption is around 10 dB per kilometer as well. One last comment on atmospheric absorption is that atmospheric absorption increases due to rain, but the impact again is insignificant at low carrier frequencies. So for instance, up to FC of less than equal to 6 gigahertz, the impact of rains, even the heavy rainfall, is negligible, but at higher carrier frequencies like at FC is equal to 10 gigahertz, the path loss, the additional atmospheric absorption due to heavy rain, increases up to 1 dB per kilometer. So this is the rain-related atmospheric absorption. By and large, the atmospheric absorption is therefore quite low or negligible at low carrier frequencies. So for instance, until 1 gigahertz or even up to 6 or 10 gigahertz, the loss is quite low, but it increases up to 10 dB per kilometer at carrier frequencies of, for instance, 60 gigahertz. Now the next topic that we are going to talk about is thermal noise, which is often characterized in terms of the noise floor. Thermal noise, as we also talked briefly in the previous lecture as well, is caused by the thermal agitation of free electrons in the conducting elements. So these are the random electron movements that are taking place in the conducting element and superimpose on the original signals that are being current or voltage signals that are being processed. So this noise or this random movement of electrons superimposes on the signal of interest. It is additive in nature and is purely random. Just like any other random variable, it is therefore characterized in terms of its power spectral density. PSD. And if you recall, any random variable that its power spectral density basically gives you a picture of how the energy of that particular random variable is distributed across the frequency spectrum. The power spectral density forms an Fourier transform pair with autocorrelation function. And if you imagine that if there is a random movement of electron that is completely independent at one instant of time to the next instant of time, then the autocorrelation function that you will get will have a single spike at a lag of 0, and there will be no autocorrelation at lags greater than 0. This corresponds to a Fourier transform pair where the frequency distribution across the frequency, the power spectral density is flat and looks like this. So this thermal noise has a flat power spectral density, which is equivalent to saying that it has an impulsive autocorrelation function. This impulsive autocorrelation function can also be interpreted by saying that there exists no correlation whatsoever between the consecutive samples of the noise or the consecutive values of noise at various instances of time. Another important property of this thermal noise is that because of the fact that this noise is caused by random movement of electrons, which are all independent and identically distributed. So IID, small random variables, add together to produce thermal noise. And as such, under the so-called central limit theorem, this noise that we get, typically denoted by eta t, will be Gaussian distributed with a particular mean and variance sigma square eta. The mean is typically 0. There is no bias in the noise that is created, and sigma square eta is therefore the autocorrelation and autocovariance, or the power of the noise. This thermal noise is characterized in terms of power spectral density. The power spectral density is proportional to the temperature, and with the constant of proportionality being k, k being the Boltzmann's constant. Sorry. And has a value of 1.381 into 10 power minus 23 joules per Kelvin. And T is the temperature of the device. The power spectral density of the noise can be given as kT, where k is the Boltzmann's constant, and the unit of this is dBm per hertz. as is typically the case. At a value of 290 Kelvin, which is considered as the standard room temperature, this evaluates to a power spectral density of thermal noise being minus 174 dBm per hertz. Now, if you imagine that the channel bandwidth, the bandwidth of interest, is B, then the total power then the total noise power that corrupts the signal of interest can be given just like the case of any power spectral density. If we just multiply it with the bandwidth, and then we get the total power that is spanned by that particular bandwidth. The total noise power P noise can therefore be given as K times T times B, and this can also be expressed in the units of dBm. 10 log 10 of K times T plus 10 log 10 of B. 10 log 10 of KT at T equal to 290 Kelvin amounts to minus 174 dBm per hertz plus 10 log 10 of bandwidth. So if we have, for instance, a bandwidth of 1 kilohertz, that would lead to this quantity being 30, and that would mean that the total noise power that will be coming in to this 1 kilohertz of bandwidth will be minus 144 dBm. Similarly, if the bandwidth is 1 megahertz, it will be minus 114 dBm of noise power. Now, going further, the next topic that we are going to discuss is the noise figure, NF. Noise figure basically determines or helps us to characterize the additional noise that is added by any component or by any subsystem or the complete system for that matter. It is typically characterized by the carrier to noise ratio at the input of a particular block versus the carrier to noise ratio at the output of that block. So if we imagine that there is some signal which is fed to some black box, and if we evaluate the CNR, the carrier to noise ratio at input, and the CNR, carrier to noise ratio at the output, and take the ratio of these two quantities, that is NF is equal to CNR at input divided by CNR at the output. Carrier to noise ratio, as we mentioned probably also in the previous lecture, is basically the ratio of the carrier power to the noise power at any stage of the RF circuitry. And this black box that we have drawn here can be a particular component, like for instance an amplifier or a filter or any other component. And just by comparing the CNR at the output by CNR at the input, we get the noise figure of the particular system. This noise figure can also be, by the way, expressed in the units of dBs. NF dB will be equal to 10 log 10 of this ratio, which will be CNR input minus 10 log 10 of CNR at the output. Therefore, this will be the CNR input in the units of dBs minus the CNR output in the units of dBs. So it is basically therefore the additional noise or the degradation of the SNR of the carrier to noise ratio that is caused by that particular component. Any component or any subsystem in the context of RF front ends can be interpreted as a block that introduces some gain, or for that matter a loss, and this amplification or attenuation block, any block, will not only amplify the signal that appears here, but also the noise that appears here. So both the signal and the noise at the input will be amplified or attenuated by the same factor. Under ideal circumstances, that this black box adds no additional noise, even with this particular gain or loss, amplification or attenuation being added by the block, the CNR at the output, the ratio of carrier power to the ratio of the noise power will stay the same. So a noise figure of 1, or a noise figure equivalently, a noise figure of 0 dB corresponds to an ideal block which does not degrade the carrier to noise ratio at the output as compared to the carrier to noise ratio at the input. And it can be still an amplification or attenuation block. But in general, the real life components, the real life RF components or the complete subsystems will always add some additional degradation, additional noise into the signal, which will degrade this carrier to noise ratio at the output as compared to the carrier to noise ratio at the input, leading to a noise figure value which is always greater than 1 or greater than 0 dB. This can be visualized as well. So if, for instance, we consider this system, which is introducing a gain of G, that is multiplying the input signal with a factor of under root G, and the input signal here is S of t plus eta of t. If we evaluate the CNR at the input of the block, it is the power of the signal, which we label here as sigma square S, divided by the power of the noise, which we label here as sigma square eta. So this will be the CNR at the input. Now, after multiplication with this factor, we will have here a signal which is under root G times S of t plus under root G times eta of t. But as we just discussed, each component adds some additional noise into the signal, and we let this noise being denoted as eta dash of t. So that we can write that the signal here at the output will be equal to under root G times S of t plus under root G times eta of t plus eta dash of t. And now if we want to write the CNR at the output of this block, we can see that the signal power now is basically G times sigma square S, and the noise power is G times sigma square eta plus the noise power plus the power of this noise, which we call as sigma square eta dash. And if we take out the common parts, we'll see that this can be expressed as sigma square s divided by sigma square eta plus sigma square eta dash divided by g. Now this was basically a hypothetical block which adds an amplification by a factor of g and adds some noise to the signal after amplification before feeding out the output. The noise figure of such a system can therefore be defined as the ratio of CNR at the input, which will be sigma square s by sigma square eta, divided by the CNR at the output, which is basically g times sigma square s divided by g times sigma square eta plus sigma square eta dash. And if we do some simple maths by cancelling out sigma square s in the numerator and denominator, and taking g common at the denominator, we are going to end up in the following expression, that we'll have 1 plus sigma square eta dash divided by g times sigma square eta. And this will be the noise figure, and because both these quantities sigma square eta dash and sigma square eta and g are all positive numbers, we can readily see that noise figure of any system will always be greater than 1 on a linear scale, and it will be equal to 1 if and only if sigma square eta dash is equal to 0. That is, this particular block adds no additional noise besides just the amplification of the signal. So this is the concept of noise figure. By the way, in certain applications like satellite communication, the noise figure property of any component or the subsystem is also described by an equivalent quantity, which is referred to as the equipment temperature. Mathematically, the equipment temperature is defined as follows. T equipment is equal to T naught times NF, the noise figure of the system, minus 1. So the amount of noise figure that exceeds 1 is multiplied with T naught to get the equipment temperature. And this equipment temperature represents basically the additional noise that is being added by that particular component. Now, proceeding further on the topic of noise figure, we also need to discuss briefly the noise figure of a cascaded system. So we are basically going to discuss that if there is a chain of components with which are interconnected, one following each other, each of these modules have some individual values of noise figure. How does the noise figure of the overall chain or the cascade of these components look like? So to discuss this, we will draw a diagram like this, where we have components like G1, then we have the second component adding a gain of G2, then we have the third component adding a gain of G3, and Before winding up the topic of noise figure, I would also like to discuss the noise figure of a so-called cascaded system. By cascaded system, we refer to a system that consists of multiple components that are interconnected to each other. Each of these components has some gain associated with it, and the gain may well be less than 1 to reflect a lossy component to produce the final output. So we say that this block, the first block, has a gain of G1 and a noise figure of NF1. The second block has a gain of G2, which may well be less than 1 to indicate a lossy component, and a noise figure of NF2. The third component has a gain of G3 and noise figure of NF3. The fourth component has a gain of G4 and a noise figure of NF4. And the basic question that we are interested in right now is we are very clear that the total gain of the system will be equal to G1 times G2 times G3 times G4. But what will be the total noise figure of this particular system is basically the question of interest. So we say that G total is equal to G1 times G2 times G3 times G4. The noise figure of the total system is what? So that is our main interest, and it can be shown through very simple means, algebraic means, and it's very similar to the way we computed noise figure of the system on the previous slide. Can be expressed as follows: NF total will be equal to NF1 plus the noise figure, which means the noise figure of the first element, plus the noise figure of the second element minus 1 divided by G1, where G1 is the gain of the chain up to this point, up to the input of the second component, plus NF3 minus 1 times G1 times G2. That is gain G1 and G2 multiplied together to provide the effective signal gain at the input of this block. The noise figure of this particular block contributes to the overall noise figure by this factor, NF3 minus 1 divided by G1 plus G2 plus NF4 minus 1 divided by G1, G2, and G3. And plus this may, of course, continue if there are further components in the chain. The most important property that you can readily see from this expression is that the overall noise figure cannot be less than the noise figure of the first component, which is being added to the total noise to arrive at the total noise figure without any division by any gain factor. All the subsequent noise figures are subtracted by 1 and then divided by G1 or G1 times G2 or G1 times G2 times G3, depending upon their placement in the overall chain. So we can readily see that the overall noise figure of the cascaded system cannot be less than the noise figure of the first component. The noise figure of the subsequent components is downscaled by the amplification factors that are there until that component. So if we therefore want, and because we naturally want to have a low noise figure for the overall system, what we do typically is to use the first component in the chain to have very low noise figure, and it must have a large gain such that the noise figure of the remaining components is uh, sufficiently downscaled before being added to arrive at the total noise figure. And that is why the first component that we use should have a sufficient or a moderate amplification, but especially low noise figure. Such a component is referred to as low noise amplifier, LNA, and as its name suggests, this component performs some amplification. This amplification might be moderate, only around 10 or 20 dB, but it does this amplification with a very low value of noise figure, such that the remaining subcomponents G2, G3, and G4 can provide the remaining gains even with higher values of noise figure, but it still lead to a sufficiently low noise figure of the complete system. Before we proceed further, I would like you to please try and work out an example with some selected values of G1, G2, and G3, and to see how does the overall noise figure of the system can be computed. To give you an example, let's say I would write G1 is equal to 20 dB, and the noise figure 1 is 2 dB, for instance. G2 is equal to minus 1 dB, which may well be a filter with an insertion loss of 1 dB, and the noise figure of this filter module is high, let's say 6 dB. Then we have another amplification block which have a high gain of 40 dB and a considerably higher noise figure as well, so let's say 10 dB. Then we have the fourth block, which is again some filter of some moderate insertion loss of minus 1 dB and a noise figure of, let's say, 15 dB. And I would like you to please compute not only the total gain of the system, but also the total or the effective noise figure of this system by the means of this formula that we have just written, and see and appreciate that just because of this component, which has a very low noise figure as compared to the subsequent components having 6 dB, 10 dB, or 15 dB of noise figures, the overall noise figure of the system will not be dominated by these subsequent terms. Now, one last topic that we need to discuss before we can start the discussion of receiver sensitivity and the link budget analysis is required CNR, or the required carrier to noise ratio. The required carrier to noise ratio can be interpreted as that particular carrier to noise ratio at the RF output of the receiver at which the baseband receiver can reliably decode the information signal. So this of course depends upon the modulation scheme and upon the coding scheme that is being used in a particular radio. Because you can probably recall from your basic courses of digital communication or wireless communication, we typically have curves like SNR versus BER curves that look like this. There are some modulation schemes like, for instance, BPSK or QPSK Then there are some other modulation schemes that provide the BAR at much higher values of SNR, and there are some even higher order modulation schemes that provide the same level of bit error rate at even higher values of SNRs. So this particular modulation scheme could be BPSK slash QPSK. Then there will be some modulation schemes like 16 QAM, and this modulation scheme of 64 QAM or 256 QAM that will require a very large SNR in order to arrive at the same particular BAR, reference BAR level. If, for instance, we define the reference BAR to be this value, and we read the x-axis corresponding to this particular modulation scheme, and for instance, let's say I know that in order to reach a BAR of 10 power minus 5, and the BPSK and QPSK modulation schemes typically require an SNR of 9 dB. That would mean that the minimum required signal to noise ratio for the baseband receiver to be able to successfully decode the message with a bit error probability of 10 power minus 5 would be around 9 dB. And how does this relate to the carrier to noise ratio? The carrier to noise ratio can be expressed as CNR required is equal to SNR required plus some losses of implementation. So this figure of 9 dB comes from the theoretical curves. But of course, under practical implementations, because of finite point precision and because of some issues in parameter estimation. So for instance, if the channel is also being estimated, if the noise power is also being estimated and used by certain modules of the receiver, there can be imperfections in the channel estimation, there can be imperfections in the noise power estimation, and these imperfections lead to some further degradation of performance, and therefore whatever SNR we require from the theory needs to be sufficiently upgraded by some loss of implementation loss factor. So for instance, an implementation loss of around 2 dB can be assumed to lead to a particular requirement on the carrier to noise ratio. By the way, in the context of direct sequence spread spectrum systems, there is something referred to as processing gain. Processing gain is abbreviated as PG and is equal to the ratio of chip rate to bit rate. In the direct sequence spread spectrum systems, you may recall that a given bit sequence is multiplied by a very high rate chip sequence, which leads to spreading of its spectrum. And the ratio between the chip rate and bit rate is referred to as the processing gain. The processing gain, for instance, can be, is typically a factor of 2. So let's say a processing gain of 128 would be quite reasonable in the context of 3G communication systems, WCDMA systems. This processing gain means that the spectrum, the spreaded spectrum, will be 128 times lower in its height as compared to the de-spreaded spectrum, which will be attained after multiplying with the correct chip code sequence. And in this context, the carrier to noise ratio can be much lower, but after multiplication with the right with the correct orthogonal sequence or the chip sequence, the signal gets de-spreaded, its spectrum rises above the noise floor and leads to a boost in the signal to noise ratio. So in the context of direct sequence spread spectrum sequence, we will also have a factor which is minus 10 log 10 of processing gain PG in this overall expression. So if you require, for instance, an SNR of 9 dB plus an implementation loss of 1 dB, that is 10 dB of SNR, and if there is a processing gain by a factor of 100, we can easily have a carrier to noise ratio of minus 10, and after benefiting from the de-spreading, that will correspond to an SNR, required SNR of plus 10 dB. So this is the overall formula that we typically use for SNR for computing the requirement on the carrier to noise ratio. This term is coming from the theoretical BAR curve for the particular modulation and coding scheme. This is the implementation loss, and this is the processing gain, which is relevant only for the direct sequence spread spectrum systems. Now, going further, we are all set to now formally define the receiver sensitivity. The receiver sensitivity refers to the lowest magnitude of received signal, the lowest received signal power at the input of the receiver that would lead to a successful decoding of the messages of the information message at the receiver. And as you can well imagine, this will be then determined by the thermal noise floor of the system, by the channel bandwidth over which the signal is being processed, the noise figure of the entire receiver subsystem, and finally, the minimum required carrier to noise ratio that we just discussed. Mathematically speaking, we define the receiver sensitivity as follows. In the units of dBm, can be written as 10 log 10 of kt, which is in the units of dBm per hertz, plus 10 log 10 of bandwidth, which then adds to produce. This is basically the noise power or the noise floor of the receiver. Then we add to it the noise figure of the receiver, the total noise figure in the units of dB, and we add to it the minimum required CNR in the units of dBs. All these quantities added together will produce the output, will produce basically the signal power which you must provide at the input of the receiver in order to ensure that the message is successfully decoded. So this is the noise power. This is the added noise power by the system. This is basically the total noise power, and this carrier to noise ratio required dB is basically is added to this noise power to ensure that this signal, once provided at the input of the system, will finally arrive at the output of the receiver subsystems with the sufficient CNR that is required in order to reliably decode the messages at the receiver. This can also be written as 10 log 10 kt is typically written as minus 174 dBm per hertz plus 10 log 10 of bandwidth plus noise figure in dBs plus the CNR in dBs, CNR required in dBs. As an example, I would like that you compute the sensitivity of a receiver with bandwidth of 25 kilohertz. This is in the context of tactical or military communication. This is typically referred to as a narrowband system. 25 kilohertz is a standard bandwidth of narrowband transmissions. System noise figure of, let's say, 8 dBs and a CNR required of, let's say, 10 dB. If for a particular modulation and coding scheme that is being used over this narrowband channel of 25 kilohertz, if you require this carrier to noise ratio to be at least 10 dB, and if the noise figure of the overall system is 8 dB, what is the sensitivity? What is the minimum signal power that you can feed into this narrowband receiver and still be able to reliably decode the information message? And then the second question is, how would the sensitivity change if we go to a wideband receiver with bandwidth equal to, let's say, 2.5 megahertz instead of 25 kilohertz? The noise figure and CNR requirement stay the same. And what is the sensitivity now? For this particular wideband signal. So these calculations will help you understand the terms better, and I would therefore encourage you to do these calculations at in your notebooks. This will indicate, for instance, that if we increase the bandwidth of the signal by a factor of 100, how would the sensitivity of the system change? Now, finally, I would like to talk about the link budget equation. The link budget, as we discussed at the start of the lecture, takes basically so this was, I guess, heading number H, and we are going to talk about now the link budget analysis. The link budget analysis takes into account the receiver sensitivity that we just defined, and the receiver sensitivity in itself took into account the temperature of the device, the bandwidth of the channel, the noise figure of the receiver, and the CNR required. So all these components have been discussed in today's lecture. The receiver sensitivity, then it takes into account the transmit power and antenna gains. It also takes into account all types of propagation losses. So this includes not only the free space path loss plus path loss, real life path loss, plus any other atmospheric absorption or any other signal loss due to other factors during propagation. So link budget analysis will then be used. By taking into account the combination of these, it will be able to tell us whether for a given transmit power with given antenna gains, would the propagation loss be so high to lead to a signal that is weaker than the receiver sensitivity or not. It will therefore be able to tell us that will a communication link under particular settings of TX power, antenna gain, and propagation losses be able to provide the receiver with a signal that is higher than the receiver sensitivity in order to ensure that the link would work or not. We therefore define the link margin as the received power in dBm that we are going to receive at the receive antenna minus the sensitivity that we in dBm that we just defined on the previous slide. The difference of these two is referred to as link margin. And if this difference is negative, that means that the received power is less than the sensitivity of the receiver, then we are sure that the receiver will not be able to reliably decode the messages that were sent. So it's very clear, link margin of less than 0 indicates that communication link will not work. And I think it should be clear, but let me also give you an example. Let's say we have the sensitivity of the receiver as minus 100 dBm. And if the amount of received power that we get by taking into account the transmit power, the antenna gains, propagation losses is, let's say, minus 105 dBm. In that case, minus 105 minus 100 will be equal to minus 5. And this link margin of less than 0 would mean that because the received signal is lower than the sensitivity, the communication link will not work. On the contrary, if the link margin is greater than 0, then this is a prerequisite. We can talk like this, that this is a prerequisite for the communication link to work, because the received signal power is higher than the minimum signal power at which the receiver is designed to operate. But in a real-life environment, the link margin is typically desired to be a sufficiently high value and then 0 dBs, because of the fact that we would like the receiver to be robust against. So let me write that a positive value is a prerequisite for receiver to work, and large positive value is desired in order to ensure that the link is working, even if some of the assumptions that have been used in the analysis are violated. So for instance, if the assumption of the atmospheric absorption taken as, let's say, 0.1 dB per kilometer is is violated because of the fact that the humidity is high, or because of the fact that there is a heavy rain going on, or any other factor, if there is some unforeseen additional loss due to, let's say, for instance, the path loss exponent in a particular environment exceeding the assumed values, a large value of link margin would ensure that the communication link still works. A large value of link margin would also be desired if we want the communication to be prone to what we refer to as fading in wireless communication, channel fading. Channel fading is a concept which means that the channel gain is fading either across frequency or along time. The channel fading occurs across frequency for wideband systems, where the channel gets into a deep fade over certain frequencies as compared to the other frequencies, or the channel fading occurs in time domain, where the channel is time varying and sometimes enters into a deep fade because of destructive interference of various components. In either case, there is a channel for wideband signal transmission, or a channel which has high mobility scenarios. A large value of link margin is needed to have robustness of the communication link performance. So with that, we are almost at the end of the lecture of today. I would like, before concluding, I would like to write a note for you that please see example 4.6 in the reference book, and I would also provide you the exact page number of the book that I would like you to look into. And this example will help you understand that how does the link budget analysis is carried out, and how we can predict whether or not a particular communication link would work or not for a given particular modulation scheme, for a given assumptions of propagation losses. So thanks for your time, and thanks for listening. Inshallah, we'll see you in the next lecture.